I know this is the day that you have been waiting for, the day we study earthquakes. So we have talked so much um, about the crust, the Earth's crust, and the different rocks that it forms, as well as how those rocks are changed over time, as well as all the crust in general, as far as plate tectonics, how the plates move, what happens when they move, why they move, what we call the way they move. Now it's time to study some of the natural disasters that go along with the lithosphere. Today, we're studying earthquakes. The next couple days, we're going to study our volcanoes. So I hope you are ready for a couple of very exciting lectures. But to start us off, earthquakes. Our bell ringer this morning was to explain how the crust can be deformed. We learned about this yesterday. What is one way? What are some things that could happen? I hope the words fault, fracture, or break were flashing through your mind. We can stress our rocks out depending on whether we're compressing, causing tension, or sliding past one another. And those different stresses can deform the crust. We could sometimes fold them. We could break them, but not move them in a fracture. Or we could break them and one could slip up or down depending on the type of plate movement that we are experiencing. That's how the earth can be deformed. It all has to do, though, with the movement of the tectonic plates. And then predict for me what it feels like to undergo an earthquake. Hopefully you were able to tell me that the ground is shaking, things might fall off the walls or shelves. Sometimes if they're severe enough, they can destroy buildings as well. But earthquakes are what we're studying today. And although we don't live in a very earthquake-present place, we don't really get earthquakes here. We get one. I've been in one really small one here in North Carolina, but for the most part, we really don't get them. But they can be really dangerous, like out on the West Coast at the San Andreas Fault that we talked about yesterday. The earthquakes can be quite dangerous. Today we're going to dissect an earthquake, and see how it moves and why it happens. So as far as what causes earthquakes, the vibrations of the Earth's crust are what cause an earthquake. This usually occurs when rocks under stress suddenly shift along a fault. So we learned that the stress of a rock is caused by the movement of the tectonic plates. But what you didn't know, or maybe what you didn't realize, is that as we stress those rocks, they're going to reach a point where they move. So an earthquake happens when plates overcome friction and move. So during that first initial, and it's like if you were trying to push a really heavy friction. So hang on, let's talk about friction for a second. So whenever I think about friction, I think about my weightlifting days. I used to be a swimmer, so we hit the weight room. But anyways, one of the activities we did was a sled. So you'd sit somebody, like one of your teammates, on a sled, and you'd be on the carpet. And usually the teammate would be either like one really like large muscular person or a couple people sitting on each other's laps. And then your job would be to move the person from one side of the room to the other side, to slide them along this sled. But if you've ever tried this before, it would be like pushing and they don't move yet. The friction has stuck them to the ground. They haven't moved. You haven't overcome the friction force. So the rocks can experience stress, but not overcome the friction. So they might not move or fold until they move and overcome that friction, that force. They're not going where we won't have an earthquake. The earthquakes happen when those plates snap back into place or overcome that friction. We're going to look at a diagram and it'll make more sense in a second. The elastic rebound theory is what we credit or how we say earthquakes form. So the first step is stress builds up between two plates that are locked into place by friction. So this would be like if you put your hands together and right before you're able to slide them up and down, right before that force that you feel is friction. Eventually, plates will overcome friction, causing the plates to move, which causes our earthquake. But after we have an earthquake, our plates snap back into place or in their former shape, and that can cause what we call a rebound quake, or an afterquake, or an aftershock. So here's what happens. We've got a transform boundary right here, which is when our earthquakes happen. Rocks on each side of the fault are forced to move, but the rocks are locked into place. This is transformed because they're sliding horizontally next to one another. One plate moves one way and one moves the other. Right now, because they have not overcome friction, they are locked together. Eventually, the rocks bend a little bit because we're putting so much pressure on them. But they don't let go yet. They're coiled. It's like if you coiled a spring. They have a lot of potential energy. Eventually, that force is going to be so much that they can't hold on any longer. And the moment they snap apart or let go or spring back is what causes the earthquake. We have, so that's why it happens. We need to look at the different parts of an earthquake. So there's a lot of parts, but the focus is the first part we're going to talk about. It's the point on the fault at which the first movement occurs. This is above this is inside the earth, a little bit down in our crust. The epicenter is the point on the surface directly above the focus point. This is on the surface. So we could stand on an epicenter of an earthquake. We could not stand on a focus of an earthquake because it's inside the Earth's crust. So if you see right here, we've got two plates that we're sliding past one another, and we're going to do a diagram on this too to help make it help you understand a little bit more. But the focus is down in between the crust where the earthquake actually happens, and the epicenter is the point on the surface directly above it. We have three types of seismic waves, but we can collect them all together. Excuse me, that was wrong. They're all called seismic waves, but we have three ones. Seismic waves pretty much is the vibration of the earth, and it radiates out in all directions. So if you see, the seismic waves are these right here. We have three types, but they radiate out in all directions. We're going to look at those three types. The three types of seismic waves are primary waves, or P waves. This motion is a compression and stretching of material. P waves move through solids and liquids, and these are the first waves recorded by a seismograph, or what measures an earthquake. They're called P, or primary, because they are the first. Our S waves, or our secondary, move in a side-to-side motion, and we're going to look at a graph on this, or chart, so it's going to make more sense. They can move only through solids, so you will not experience S waves if you're on the ocean. These are the second waves recorded by a seismograph. That's why they're called secondary. When P waves and S waves reach the surface, they become L waves, or long waves, surface waves. They move more in a rolling motion. They can only travel on Earth's surface, and they are the last to reach the seismograph. They're slow, and these cause the most damage. P waves are so fast that they travel twice as fast as our S waves. So, I know this is a little distorted, but this is what our waves look like on the Earth. So you can see our primary waves right here. They move in a horizontal direction, so they are compressing and releasing, like a not a xylophone, what's that thing called? Accordion. There we go, that musical instrument. Mr. Lovett showed a video the other day of how to make one. But anyways, like an accordion, so they're pressing in, squeezing together, releasing, squeezing together, releasing. S waves move in an up and down motion, so they move more like the wave. Up and down, you can see. And then our L waves, or our long waves, move in all directions. So they move side to side and a little bit up and down. Again, L waves cause the most damage. Seismographs are the instrument that detects and records earthquake waves. They record first the up and down motion, they record the east to west or side to side motion, and they can also record north to south motion or side to side. Seismographs not only record the measure of the waves, but they can help locate the earthquake. Where did it start? Seismographs can tell how far away the epicenter is. If we have 3 of them, we can determine the exact location. If you've ever watched a CSI show or something like that, you know that they can triangular locate a phone call. Same type of thing happens with seismographs in locating the epicenter of an earthquake. Seismographs can also be used to determine the strength of a quake. The larger the number, the more damage the quake can do. This is what a seismograph looks like. You probably won't see one in your lifetime, but if you do, take a picture and send it to me because I think they're pretty cool. So the spring is what moves up and down. There's a pen right here tracking the, or indicating the movement of the wave. And then somebody reads this off, somebody with a lot more experience than me, and can tell you how strong something is. Seismograph. This is an example of what you might see. So you're going to see the P waves first, and then it's going to be a while, and then you'll see the S waves, and then we'll see the long waves. The time between the P and the S is the proportion to the distance from the focus, or the middle of the epicenter. So we could use this to help locate where the earthquake is in the center of the earth. We're going to skip this one. So if we were looking at this, the size of the line, or the space in between the P wave and the S wave, helps us indicate how large the earthquake is. The more space in between those P waves and the S waves, the larger the earthquake is. Not something I necessarily test you on, but something you might want to know. Again, if we want to triangular locate, we would use some math, which, by the way, math is super important, and 3 seismographs. We don't have to learn too much about that. Richter scale is actually what we use to indicate the magnitude of the quake. It's the amount of energy that's released. It's a scale of 1 to 10, each number representing 32 times stronger than the previous number. The higher the number, the stronger the earthquake. We also use the Mercalli scale and the Rosie-Forel scale. These are also used to measure the intensity of the quake. They're usually measured upon observing the damage done. Normally, though, you're going to hear it in the Richter scale. And then we've got this diagram to do, and it's probably going to cut off on me, so we're going to probably have to have a second lecture. But just a reminder about our waves of our earthquake, and this is a diagram. This is a chunk of the Earth's crust. And so we've got our 3 different types of waves again. Just to review, this is a chunk of the Earth's crust, and here is our boundary line right here, the fault or fracture. We're going to look at these notes though. First, let's go over the waves. Remember, P wave is our primary wave, and again, these are on your notes, so let's do these as well. These are push and pull waves. Remember, we're talking about compression here. It is the fastest wave, that's why we call it the primary. Number 2 are S waves. They move up and down. They're secondary because they happen second. They are slower than P waves. We call these transverse waves because they move at right angles to the direction of travel because they move up and down. And lastly, if you remember, our surface waves are L waves. These are the most destructive. They arrive last and they cause the ground to actually move. They move up and down and side to side more in a rolling wave type motion. If you look right here, our P waves are compressing the ground and releasing. Our S waves, you can see that up and down movement, and the surface waves here are more of a rolling movement. Again, these are the ones that are going to cause the most damage right here. All right, so some things to label on your notes. Focus is the blue part, the center. And you might have to put some text boxes in here, and that is fine. The focus, again, is the center, and I've got 2 little blue dots. I've got one without lines and one with lines. We'll catch you next time on the next lecture.